IPv4, or Internet Protocol version 4, is the backbone of computer networks. IPv4 is the fourth iteration of the Internet Protocol and the first version to be widely deployed. It serves as the foundational protocol for Internet communication, enabling devices to identify and locate each other on networks worldwide. An IPv4 address is a 32-bit numerical label assigned to each device connected to a network that uses IP for communication. It is typically represented in dotted decimal notation, consisting of 4 octets separated by periods, for example, 192.168.1.1. An IPv4 address is divided into two main parts: the network portion, which identifies the specific network, and the host portion, which identifies the individual device within that network. The division between the network and host portions is determined by the subnet mask. Historically, IPv4 addresses were categorized into classes A, B, C, D, and E based on their leading bits, but modern networks use classless interdomain routing for more flexible and efficient allocation. Subnetting is the process of dividing a larger network into smaller, more manageable subnetworks. This enhances routing efficiency and improves network security. By adjusting the subnet mask, network administrators can control the number of possible subnets and hosts within each subnet. Routers use the network portion of an IPv4 address to determine the best path for data packets to reach their destination. Routing tables store information about network addresses and their associated paths, enabling efficient data transfer across interconnected networks. Protocols like OSPF and BGP facilitate dynamic routing based on current network conditions. Due to the limited number of IPv4 addresses, approximately 4.3 billion, address exhaustion became a significant issue as the Internet expanded. To mitigate this, techniques like network address translation were developed. NAT allows multiple devices on a local network to share a single public IPv4 address by translating private IP addresses to a public address for external communication. IPv4 addresses are traditionally divided into classes based on their leading bits. Class A supports approximately 16 million hosts per network, Class B supports around 65,000 hosts per network, Class C supports 254 hosts per network, Class D is reserved for multicast, and Class E is reserved for experimental use. The limitations of IPv4 include address exhaustion, security vulnerabilities, and fragmentation. The finite number of IPv4 addresses limits the growth of the Internet, necessitating address conservation methods like NAT. IPv4 was not designed with robust security features, making it susceptible to various attacks, and security is often added through additional protocols like IPsec. IPv4 can lead to packet fragmentation, which may degrade network performance and complicate data transmission. To overcome IPv4's limitations, IPv6 was developed, offering a vastly larger address space with 128-bit addresses. While IPv6 adoption is increasing, IPv4 remains prevalent due to its established infrastructure. Transition mechanisms such as dual stacking and tunneling facilitate the gradual shift to the newer protocol. IPv4 has been instrumental in the development and expansion of the Internet, providing essential addressing and routing capabilities. Despite its limitations, especially regarding address exhaustion, IPv4 continues to function effectively through various conservation techniques. The ongoing transition to IPv6 aims to address these challenges, ensuring the scalability and security of future networks.